What we going to do? What you gonna do? We are going to do this. Let's see our course outline here. We're falling behind a little bit. Today we're still in week 3. We didn't start the Cmos logic gates, an intro to HDL yet. So I'm going to go over assignment 1 first. Then we're going to go back and we're going to finish these logic gates. Then we're going to have some bonus questions, and then we're going to move on to the next set of lectures. That is the plan. So first, we're going to go over this assignment quickly. So this was assignment 1. Ooh. Definitely don't like this new feature of Zoom. Anyway, it's due 2 weeks from today at 12 p.m. But if you go look on the webpage, I'll give you extra 5 minutes. You have like till 12:05 a.m. on the day after, 2 weeks from today. Let's see. Question 1 is design a 5-to-1 multiplexer as inputs A, B, C, D, E. It has 2 control signals and it has an output Z. So, this thing looks like this. It's a 5-to-1 mux. 1, 2, 3, 4. We'll need 3 control signals. Sorry, not 2. Right? We need 3. We need 2 for 4, but since we have 5 inputs, we need 3 control signals and 1 output like that. First, you're going to implement it with Cmos, NORs, and NANDs and inverters. So just using basic Cmos gates, right? We learned the basic 3 gates are the NOR, the NAND, and the inverter. It can be 2 input, 3 input. You can make whatever number of inputs you want for the NOR and the NANDs. Part B is implement it using a Cmos transmission gate. So we did a 2-to-1 transmission gate last day, right? Or we looked at it. Oh, sorry. Yeah, this was a 2-to-1 mux. Now you got to build a 5-to-1 mux. So you kind of like an expansion of that circuit. Using transmission gates, and you'll need some inverters as well. And then part C is which approach is better. So I want you to tell me if one is better than the other, why? Part 2 says design a 1-bit half adder with inputs A, B, and outputs sum and count. So half adder has like A, B. You're adding A and B together, right? And you get some sum, and you get an output, carry out. A full adder would have a carry in. This is a half adder, only has a carry out, no carry in. So first, use it with basic inverter, NORs, and NAND. So again, use the basic gates. B is do it with a complex logic gates. So we learned about complex gates. We kind of combine ANDs and ORs and inverters together. Hopefully you're able to reduce the number of transistors. Compare the different transistor counts. D, assuming all transistors are the same size and Kn equals 2 times Kp. So the mobility of electrons is twice that of the holes. Which version of the function do you expect to be faster and why? So this requires a little bit of explanation. So let's say I had 2 inverter, or let's say I had an inverter and I had a NAND gate. Like this. And for now, let's not worry about the other connection to the NAND gate. If I were to just approximate the delay here, I could assume kind of like 2 cases here. If the input was going from 0 to 1, I'd have this going low, and I'm assuming this goes low and this goes high, right? So in this case, I would have 1 N channel here, delay, and pulling up, I would have 1 P. So I would say the total delay of this is 1 N plus 1 P, and then I'd have to factor in the mobilities to say what the total delay is. I'd multiply by the mobility. So the P's would be like equivalent to 2 N's, right? So this is like 3 N's in this case. What about the other direction? Because I got to figure out the worst case. If this was going low, this would go high, right? So this would go high and this would go low. So what have I got in this case? Then I would have 1p plus, and then pulling low, I would have 2 n's, right? And this 1p is like 2 n's, so that's like 4n. So the worst case situation for this circuit would be like the equivalent of 4n delay. So you got to kind of use that same principle for your circuit for the half adder. It'll be more complex than this, but you got to kind of figure out what's the worst case delay I can have in this as a kind of a crude approximation. And what you're doing is you're comparing the basic gates versus this complex gate. And hopefully if you make the complex gate well, it'll have less delay, one would hope. Okay. Part 3 says you have a complex gate which has this functionality. G equals, it's a function of A, B, C, D, E, and F. And you have a 0.8 volt supply voltage, a low capacitance of 0.25 femtofarads or 250 attofarads. Assume all transistors are in saturation during switching and have the following parameters. So you're given the widths and the lengths and the process gain factors, Kp prime, Kn prime, the VTs, lambda 0, so you can ignore channel length modulation. And this is the equation for saturation. In this case, you can kind of ignore this term because this is 0, right? So just realize VGSs in these will be either 0 or VDD. 0 when it's turned off, and it's VDD, i.e. 0.8 volts when it's turned on. And you're asked to A, calculate the worst case delay, either falling or rising delay, not average, for the complex gate. So you're building a complex gate like this. So it's going to have a bunch of, bunch of series and parallel transistors. I'm just drawing something arbitrarily here. I don't know if this is what it is, but you're going to figure out the worst case paths for pull down, the worst case for pull up, take the worst of the worst and calculate the delay. And you're going to calculate the delay using this current equation. And then you're going to, from that, you can do the delay, right, is CVD over 2I. And you're going to plug this capacitance here. You got the capacitance, you know what the VDD is. Once you calculate the I, you can calculate the delay, and you're going to figure out which is the worst delay. So that'll be just a single path will give us the worst delay. And then B is calculate the best case delay. We know from last class, the best delay is when all the P's or all the N's are on. And I want the best of the best, right? Whichever is the better of the two. All paths N or all paths P. And then C is calculate the dynamic power dissipation, assuming the gate is clocked at 2 gigahertz. So that's pretty easy. You just plug in that formula. We did the bonus question like this. We know the frequency, right? The power is FCV squared, right? And so you know the frequency, you know the capacitance. That's pretty easy. Now part D, it says, how would you change the widths of the P-channel transistor so the worst case rising and falling delays are equal? Note all transistors should have the same new width. So you're going to have a circuit here. It's going to have some P's and some N's, right? I don't know. I'm just drawing a couple of P's here if I can draw them. Something like that. I don't know, whatever it is. I'm just making this up. But anyway, there's a bunch of P's. They have some delay, a bunch of N's. The worst case is through one of the worst case paths, whatever it is. And I want to change the widths of the P. So I'm going to change these, either make them bigger or smaller, keeping all the W's the same, so the worst case rising and falling delays are equal. Okay. So that's part 3. And then part 4 says, implement the 2 circuits below, commonly referred to and or invert AOI or and invert OAI circuits as complex gates. So you're going to build complex gates. These can be built with a single complex gate. They're very commonly, a common standard cell is this AOI or OAI circuits. Verify the truth table matches the logic equation for 2 rows. You're going to use our Heisenberg principle just to make sure you got the logic gate right, because you're going to build this out of transistors. You're going to put the truth table, and the truth table should match this circuit. Just for 2 rows. Like there's a 1, 2, 3, 4. There's 16 possible entries in the truth table. Just do a couple of them and kind of make sure it makes sense. And C says, assuming all transistors have the size K, so the KNs and KPs are the same, which circuit would be slower, i.e. have the largest worst case delay? Well, that's question 4. Any questions about that?
Can you go back to the drawing that you did for question 2, I think?
Question 2 up here? Yeah.
No, you drew it on the Paint or whatever, the app.
Oh yeah, sorry. Oh, you just want to do a screenshot? Do we have a question?
Yeah, I just wanted to do a screenshot.
Oh, okay.
So the assumption in this question will be that the mobility of P is double N. Is that in like given?
No, the N is 2 times the P.
Oh,
Right here.
yes.
That's given, yep. Okay, that's assignment 1. So now let's go back and finish this set of notes. So last day we did, last thing we did was fan out.